You get it? I will begin. Ahem. 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 Let's see. 1, 2, 3, 6, 7, 8, 9, 10, 11, 12. What's that? What's 12 over 15? What we got? 80% attendance, is that right? Wait a minute, I didn't count you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13 out of 15. Ooh, there we go. That's pretty good. Who are we missing? Well, let's not name names. I will begin. So, dear Father, we thank you for this day. And I just pray that you'd be with us today. Help us to, again, Lord, glorify you what we do. And just help us to understand these tricky limits and a little bit about this improper integration. Lord, in your name I pray. Amen. Okay, so I will take your homework question in shortly. But let me just finish my talk, so to speak, here. And so we figured out that there were indeterminate forms, right? And so indeterminate forms, what were they?
0 over 0.
Yeah, 0 over 0. Infinity over infinity. Infinity minus infinity. Oh, 0 times infinity. You guys told me? 1 to the infinity. Infinity to 0. And 0 to 0. All right. So here's the story. These two, we apply L'Hopital's directly, right? These, we do algebra, then we apply L'Hopital's rule if we need to. Sometimes we don't. Sometimes the algebra is enough. And then these guys over here, I use the trick. Okay, so I take my limit that I'm trying to calculate, and I replace it with the exponential of the natural log. Let me say we're calculating limit of Pac-Man. All right. So if I'm calculating limit of Pac-Man, and Pac-Man happens to be one of these indeterminate types, what I do is I take the exponential of the log of Pac-Man, and I go from there. I call this thing star, and then I, do algebra and possibly L'Hopital's rule to figure it out. And if you think about it, there's different things that could happen there. So, it could just go to e to the number if star is actually just equal to some number, right? It could go to 0 if star tends to minus infinity, right? And it could also go to infinity if star tends to infinity, right? It could even goes to not defined if you could show star oscillated. I mean, there's all kinds of different stuff that could happen there. Everything that could happen before could happen here again, like some show. Yeah, so that's what we're dealing with. Another good example of infinity minus infinity was in your book. I just noticed it's worth taking a minute of our time. Limit as x goes to 1 from the right. And the limit is 1 over log x minus 1 over x minus 1, right? This is type what? It's type infinity minus infinity because both of those go to infinity as x goes to 1 from the right. So we can't do L'Hopital's rule, but what we can do is make a common denominator, right? So that would look like what? X minus 1 minus the natural log of x divided by x minus 1 times log x, right? This one's a little bit more exciting than the one I did in class, I cherry-picked one from the homework last time. Well, maybe not. Maybe it wasn't from the homework, but I mean from the problems at the end of the section. Now I think we're good to go. What type is this? 1 minus 1, 0. What's log of 1? Log of 1 is 0, right? So we got 0 times, it's 0 over 0. So type 0 over 0, we can apply L'Hopital's rule to. Now we got to be careful. We're looking at products. Well, excuse me, not products. What's up here? 1 minus 1 over x upstairs, right? Now downstairs, I got a product. So I got to do product rule, right? So that's log x plus x minus 1 over x. Looks like I still got 0 over 0, huh? To me, this feels like I should multiply, I should do algebra at this point. What I would do next, I don't like these fractions by x, so I'm just going to multiply the whole thing by x over x. I can do that, you know, because I'm just multiplying by 1, which is allowed, right? So multiply the top by x, multiply bottom by x. What does that give you? So here, just so we understand, multiply by x over x, which clears out the fractions. Now maybe, well, I guess we still got 0 over 0 though, don't we? But we can apply L'Hopital's rule again, because it's getting better, isn't it? Well, I don't know. It's kind of, that's funny, right? Look at, we started with a log upstairs and downstairs. Now we just got a log downstairs. Maybe one more time it'll be gone completely, right? It's kind of like we're pushing the log down. So maybe we're pushing it right off the expression next step, right? Maybe not, I don't know. That's just it's an analogy. It's not a written in stone. But I do like the derivative of the top being 1. That's simple. And downstairs, product rule. So I got log x plus 1, right? Plus 1. Now, do you want me to explain where that middle 1 came from? Why do I got middle 1? What's the derivative of product rule? So I get x times the derivative of log, which is what? 1 over x, right? So x over x is 1. So this, of course, goes to 0, and the whole thing goes to 1/2. That's a good example. It's not super difficult, but it's not quite as stupid as when I worked last class. Yep.
What did the minus change to a plus?
Oh, because this, so I'm differentiating this, and it produces both of these terms. This produces that 1. The derivative of minus 1 is just gone. Because we're L'Hopital, right, L'Hopital's rule, we differentiate the denominator so that minus 1 is essentially invisible. But we need it there to apply L'Hopital's rule to start with, right? If that wasn't there, when I plug in 1, I wouldn't have type 0. You know, it's not irrelevant. It's very relevant to the starting point. But all right, and then one more example, and then I'll take your question. So I did the exponential last class. I'll do this. This is a pretty standard example. Good to do. Sine x to the x power. How's that go? So I'll use my trick, which is, hey, that's really the exponential of the limit as x goes to 0 of the natural log of the sine of x to the x. So what I did was I passed the limit inside using the continuity of the exponential, and I just inserted, you know, exponential log, which I can do because sine x to the x is positive, so that's an identity. Exponential logs being inverse functions. I give this thing a name. It's called star. Let's work on that. So star is equal to the limit as x goes to 0 of what? Now I pull that x down, right? That's really x, natural log of sine of x, right? Now, hold on a second here. For this to make sense, I need a little bit more fine print on this example, don't I? Like this limit, as I currently have written, doesn't even make sense. We don't define negative number to a real power in here, except for like cube or fifth or something like that. Like integer, odd, negative number. I mean, I can make sense of -3 to the 1/3 power or something like that. Like this is allowed. I mean, this is equal to minus the cube root of 3 for what it's worth. But you know, if we don't talk about this though, generally speaking, for x being real. What does that thing look? What does the graph of that function look like? Anyway, don't think about it too hard. It's quite awful. The point is, to make this make sense, I should have had a plus because sign is negative for x negative. Yeah. So these missing pluses. That's important because you know sign looks like that, right? So we want to consider it like over here, right? Those are the values we're looking at now. Fine. So then it's going to be kind of the same trick we did last time. I'll bring. I mean, this is 0 times infinity. Actually, technically 0 times minus infinity. You want me to get picky? Because we're looking at log of a very, very small positive quantity, which is negative infinity, right? You guys know this? What's the graph of log look like? Right? So if you're feeding log something very, very small and positive, you're going down, 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 down. This is going to minus infinity. So we've got 0 times minus infinity. So we need to convert it to something we can do L'Hopital's rule on. The natural thing to do, I think this is the way to go. If I choose poorly, we'll find out soon. If we do that, that's one thing we can do anyway. The other thing we could do, of course, would be to leave x upstairs and move 1 over log sine x downstairs. That seems unfun. 1 over x. This is still not too bad to differentiate, right? Now we've got 0. Excuse me, we got infinity over infinity. We can apply L'Hopital's rule. And that gives us, what does it give us? Let's see, that's going to give me a cosine x divided by sine x upstairs by the chain rule and derivative of log. And downstairs I got minus 1 over x squared, yeah? Not out of the woods just yet because the top is not defined and the denominator is also not defined at 0, right? Seems to me like a good thing to do at this point would be just some algebra. So let's make it into a fraction, sort of a standard fraction. So this would be minus x squared cosine of x divided by sine x. At this point, I can see the answer is 0, but I'm cheating. So we probably should look at this as 0 over 0, right? And do what? I'll tell you my secret way of seeing this as 0 already after we're done with the regular way. L'Hopital's rule again, right? Type 0 over 0. So we got to differentiate the top, differentiate the bottom. So the top's product rule, minus 2x cosine x. Plus x squared sine x, because the derivative of cosine is minus sine. Minus minus give me plus. Downstairs I got myself cosine x. And that is harmless. See, because the denominator goes to 1 as x goes to 0 from the right, or the left for that matter. And the numerator, well, it's a continuous function everywhere. Certainly we can plug in 0. What do we get? 0, yeah. That goes, 0. Okay, once I know that's 0, I go back up to here and I say, aha, this is equal to e to the 0, which is equal to 1. The answer is 1. So in this particular case, 0 to the 0 does work out to 1, but it doesn't have to happen that way, you know. You can fairly easily see that if you just tinker with like the argument of sine x, you could make it work out to something else, right? If I took this sine x and I replaced it with like px, what would that do? What would happen if I replaced x with px? How would this calculation change? Would it change that much? If I change that to px instead of just x, right? That puts a p here and here and here and, well, I guess, yeah, here. Then I got to be careful. And then, yeah, chain rule. So p, p, p. And at some point I'm going to get into trouble. It's probably now. P, p, p. P, p. Looks like a p squared. Oh, it's still going to work out to 0. Curses. Oh well, I tried. I'll have to be more inventive to make it work out to something other than that. Oh, never mind. I'm sorry. I was trying to give you 2 examples for 1, but apparently this is just a 1 for. Sorry about that. I was getting too greedy. It is what it is. I'm doing some janitorial work here. Let's see here. Is it very disappointing? Oh, sorry. I hope you can get over it. Let's see here. Somehow I think you'll manage. Let's see here. Why is there a square out there? It's weird. Okay. Yeah. I guess I mean, for completeness, I probably should show you a infinity to the 0, 1, but, you know, whatever.
Wouldn't it work essentially the same?
Yeah. If you really understand any of these indeterminate form examples, if you really understand one carefully, you can do the rest. It's the same technique on all of them. Yep.
What was the trick they used to foresee that the limit, well, that evaluation equals 0?
Oh, yeah. So at this point, I was looking at this. I was like, wait a minute. This is actually the limit as x goes to 0 from the right of the cosine of x times x minus x divided by sine x over x. And so that by the limit laws is limit x goes to 0 from the right of minus x cosine x, which is an elementary limit. And you can, this is a limit law, provided that this limit exists, and we proved it exists last class, so that's how I saw it. But I think the way we did it is maybe better even for you guys. I mean, it's less, I don't know. I mean, is it really that much better? Maybe not. You had a homework question, I think.
Yes. We look at problem 115 in your mystery, which is
Oh, no.
7, number 110.
8.7, number 110.
It's approved. I'm just not sure how to get started on it.
Okay, so prove the following generalization of the mean value theorem. If f is twice differentiable on the closed interval, yeah, actually I think I can tell you how to do this relatively quickly. So the question is, this, he's got this identity, f of b minus f of a is equal to f prime of what? Of a times b minus a minus the integral from a to b of f prime prime of t times t minus b dt. And we're supposed to prove that's what we're supposed to prove. And what do we get? We get that f is twice differentiable on the closed interval a to b. Let's see here. I think this is just integration by parts, okay? And so what you do is just integrate by parts on, let me call it Pac-Man, because that seems to be a theme for me today. So let's try that out, if we can get away with that. So we're integrating. Now this may or may not work. I may be remembering the wrong trick, but we'll try. So what we got? T minus B f prime prime of t dt. Okay, so what I'm going to do is I'm going to look at this as being dv. I'm looking at this as being my u, right? If I do that, oh, which one am I working? I'm working on which one did you say it was? Number 10, number
115 in your mission, that's 8.7 for 10 in the textbook.
So number 110 from section 8.7?
Yes.
Yeah, okay. So you guys, that integration by parts, try it. What do you get? I'll do the easy part. du is dt, yeah. And u is, well, it is what it is. What's v? If dv is f prime prime, v is f prime, right? Now this is with bounds, so we're supposed to evaluate from a to b, and then we have to subtract the integral of v du, which in this case is f prime of t dt from a to b, right? But that is what? When you plug in b, you get 0, right? See that? When you plug in b, it's 0. What happens with a? And how about this? Fundamental theorem of calculus, or the net change theorem, whatever you want to call it. The integral of the derivative. Just the function again, right? So that's just f of b minus f of a. Parentheses. Yep. Yep. That's how that one's done. Other questions about homework, you guys? Yeah.
This isn't really about the homework, this is a general question.
Mm-hmm.
But, so I've noticed that when we're using L'Hopital's rule, when taking the derivative, there are a lot of times I think I should use the quotient rule, but I shouldn't. Can you explain like the differences and what I should use the quotient?
Right, so this is, it just goes back to what L'Hopital's rule is. So L'Hopital's rule says the limit of f over g is equal to the limit of f prime divided by g prime. So that's, I mean, that is L'Hopital's rule. So that's why we don't do it. It's just we differentiate the top, you differentiate the denominator, do it separately. Now, if you did have something like, let's see here, see if I can come up with an example which actually involves the quotient rule somehow meaningfully. Debatable. Let's see here. Limit as x goes to 0 of, I don't know. Here I'll do a silly one. Sine x over tangent x. So if I wanted to be really silly about it, I could be like, haha, well, that's really sine x over cosine x, right? And so then I could actually use the quotient rule down there. But that would be exceedingly silly, because I should really just cancel the signs and identify this as the limit of cosine and be done with it. Sans L'Hopital or anything fancy. Or, going back to tangent, my point is anytime you differentiate the tangent, there's really kind of there's a hidden quotient rule right there. How do we know the derivative of tangent is secant squared? Well, it's because tangent sine over cosine, we differentiate quotient rule, out pops 1 over cosine squared, you know? So So here's a wrong way to do this. I mean, it's not wrong. It's just it's not right. If that makes sense. This is so stupid. Look at this. So that's what? What's cosine over secant squared? Oh, it is cosine. I thought it was, I'm sorry, I was thinking it was something more exciting like, oh, but anyway, that's still 1, right? Because it's 1 cubed. Or, at the start, you could have just gone, you know what? I took pre-calculus, and I know that this is just cosine, so what's your deal, you know? And so it's 1. I mean, this is the trouble with L'Hopital's rule, is once you have it, it's kind of like having a hammer. As you know the saying, everything looks like a nail. This is a well-known saying, yes. I'm kind of encouraged by what's going on in the NFL right now. I think it's pretty awesome. We are well on our way to depopularizing sports. Do you realize how monumental this occasion is? Other people was like, oh no, we're losing our pastimes and our stress-free ways of life. Like, no, we're losing sports. Yeah, this is good. No? You guys like football, I guess. I know most people like football. Fine. Neanderthals. Anyway, sorry, yes? You don't believe in Neanderthals. It shouldn't bother you. What's that?
If you get to the point where you iterated it a few times, then you get to like, let's say 1 over 1 minus x.
1 over,
Something like that.
yeah.
Is it okay then would the right thing in that situation be to differentiate the top and the bottom, thus you get 0 divided by something and your answer is just 0, or 0 divided by -1?
I mean, I guess it could conceivably happen. I don't know. Maybe. He was imagining a hypothetical where one of the things works out to be a constant.
If you have like, so let's say you have like before it becomes 1 over 1 minus x, what is like 1x over 1 minus x squared, and it's actually instead of, yeah, and then you do it twice, and then you get 0 or something.
So like this, and then,
Or then you get 1/2, I guess. Or no, you get 0.
yeah, like that. Well,
Is that the right way to approach that?
the question is, see, the trouble, I mean, if that were possible, sure. But I don't know, like the question is, which limit are we talking about? X approaches question mark in this thought process here, right? See, to get this one, I think I'd have to do infinity. Like if I had x goes to infinity, then x goes to infinity, this is infinity over infinity. Then this goes to that, there's a minus, right? But at this point, I don't need L'Hopital's rule anymore. At this point, I'm just like, oh, 1 over minus 2 times infinity, so that just goes to 0, right? And I can't apply L'Hopital's rule there, actually. It wouldn't be right to do it, because then I don't have the right type to apply L'Hopital's rule. It's no longer 0 over 0 or infinity over infinity. I mean, this is really the answer to your question. I think the heart of your question is, we only apply L'Hopital's rule when we have 0 over 0 or infinity over infinity. And when we do that, we just differentiate the top and we differentiate the bottom separately. That's what the rule says. It's just that. Now, maybe you guys would understand it better if I'd proved it to you. But I refuse to prove L'Hopital's rule because, I don't know, it's not fun. There's like 30 different cases. See, because it's not just one rule. It's like you have x goes to infinity, minus infinity, a from the right, a from the left. And then even then, there's different kinds of limits, like limits that diverge, limits that converge, and in different ways. And like every different one of these stupid subcases requires a different proof, which is why you won't find a proof of L'Hopital's rule in its generality in calculus textbooks, because they have enough sense to not do it. Anyway, with that, let's go on. Yep.
I'm still on that proof.
Uh-oh.
Get from the second to last to the last.
Oh, from here to here?
No, on the like proof, the first one, 8.7, number 110.
Oh, here to here?
Yeah.
Oh, that's because we're integrating df dt from a to b, right? So by an f substitution, this is from f of a to f of b df, which is f of b minus, f of a.
But how did you get that minus a minus b times f prime of a?
Because when the upper bound, I plug in b, I get 0. Plug in the lower bound, I get a minus because it's the lower one. Right? We subtract the expression, and then a minus b f prime of a. It's just this.
Oh, okay.
Yeah. It's cool. I don't know, it amuses me that you can look at the fundamental theorem of calculus as sort of just u substitution, right? Well, f substitution. Anyway. All right, let us go on. You guys can ask me more questions about L'Hopital's rule, like, until the next test. As far as I'm concerned, it's fine. It's all cool. It'll keep coming up. But the next topic is improper integration, which is what it sounds like. It's integrals which are not proper. I don't know what does that mean, though? They don't sit up straight. Okay, I'll allow it. So improper integrals, they really come in two types. So here are the two sort of generic types that I see. There's the limits with plus or minus infinity bounds. All right, those are kind of like in your face, obviously improper, right? And then there's the hidden infinity problems. In other words, problems that look like they're garden variety ordinary definite integrals, but the devil's in the details. So the second type is much more insidious than the first, right? The first I can teach you pretty easily. And of course, you can also have both. You can have both together. You can have both together. But I think the best thing for me to do is just to illustrate with examples rather than giving you definitions here. So example 1. We have something like the integral from 0 to infinity of e to the minus x dx. What's this mean? So what this means, this is just a notation for taking the limit as t goes to infinity of the integral from 0 to t of e to the minus x dx. So what I just did, this is actually the definition. Yeah? What was it? What question? Oh, okay. Thought I saw a question. Limit. I can't afford to lose any more of you. I've already lost 25%. The university said that I have to have an S rate of 75% or higher. So I think that means I have to pass all of you, like it's written in stone. Right? I'm not sure we should really say that. That seems wrong. I don't know. I guess these are statistical guidelines. Anyway, so you can do this integral. This is minus e to the minus x, and then we evaluate from 0 to t, right? Calculus 1 stuff right there. Then evaluate, what do we got? What's that work out to? What does it mean?
Isn't e to the negative 0 undefined though? Because it's like negative 1 over 0.
Well, this is like e to the, this is like minus 1 over e to the something huge.
Sorry, I mean, when you're evaluating the definite integral, the 1, negative e to the negative t.
Oh, you're
plus-
thinking of my next example.
Okay.
Don't worry, hang in there, hang in there. So this goes to 0, right? And so the answer is 1, right? Let's talk about what this means graphically for a second. So the graph of the exponential, what's it look like? It starts out at 1, right? And then what's it do? At that it gets, but it, it asymptotically goes to the x-axis, right? And what this integral says is that this region has an area which is bounded. Yeah. E to the negative x. What did I say? I'm sorry. Let me just be clear. Y equals e to the minus x, yeah. So that area is bounded. I mean, in fact, and it's 1. So here we have an example of something with an infinite perimeter, right? How long is the perimeter of this area? Like 2 times infinity at least, right? Because you got the top and bottom both going to infinity. It's like at least doubly infinite. Sorry. You can go back to our kindergarten taunts about who's the most awesome, and like, I'm infinity awesome, and like, I'm infinity squared awesome, and so forth and so on. Usually we'd argue that about our dads, right? I mean, that's the typical pattern. But anyway, finite area, even though it has infinite perimeter. It's kind of interesting, right? Example 2, which I think will help with Nathaniel's question. How about this? Integral from 1 to infinity of the natural log of x dx. What's this mean? How do we define this? So it's like the same thing we just did. It's the limit as, let's say, t goes to infinity. And I mean, if you don't like t, you could do b here just the same. I'm just doing t out of habit, right? I mean, whatever you like. But the upper variable limit goes to infinity. And log x dx. Now this integral, that's going to make us work a little harder, isn't it? So do you remember what that integral was? Or do I need to work it out again? X log x minus x. That sounds right to me. We got that by integration by parts, right? Now, if you're in doubt, we can differentiate and see if it works, right? Oh, that should definitely, most certainly be a t. Thank you. Very good, very good, very good. Very good, very good. Most definitely, yes. So if you differentiate my expression inside the brackets, product rule gives me log x, and then x over x, which is 1, minus 1, 1 minus 1, 0, left with the log x. Differentiate, get back to the integrand. Good. You guys told me right. Now I have to do the evaluation, right? So we do the evaluation. What do we get? We get t natural log of t, right, minus t, and then looks like plus 1. Because log of 1 is 0, right? Let's see here. What kind of thing are we looking at? We're looking at infinity. Oh, you got to be careful, right? This is what? This is infinity minus infinity, isn't it? So I should be careful here. we can rewrite this. We can factor one of those infinities out, can't we? This is t times the natural log of t minus 1, right? Which, oh, I'm sorry, plus, plus 1, right? And so that should be the limit as t goes to infinity of natural log of t minus 1 over 1 over t plus 1. Here's the thing. If the limit that I just wrote diverges, the divergent integral plus 1 still, the divergent limit plus 1 still diverges. On the other hand, if the limit is convergent, then it's that whatever it converges to plus 1. So like, this is a reasonable step to make. If you've got a constant, you can pull it out like that, even if you don't already know. Let me not belabor this point. So as t goes to infinity, what happens? We got, oh yeah. I'm sorry, I didn't need to write anything more. I'm a doofus. Let's see here, technical. Sorry, that was unnecessary. That's enough. Why is that enough? Yeah.
Like, wait, so if it goes to a constant, it doesn't necessarily convert?
The other thing might not converge. If the other thing goes to infinity, infinity plus a constant is still infinity, right? If the first thing had went to 3, then it would have been 3 plus 1 would have been 4. Like, there's no ambiguity with the plus 1, whatever, it's just riding along, so to speak. Yeah. But this is not that, because this is infinity, right? And this is infinity minus 1, which is still infinity.
But this is a different definition of convergence or divergence than like there on
Yes. We're considering a real t as opposed to a... That's tomorrow. Wait till tomorrow. Yeah. So tomorrow we start sequences. Yes, I know. Maybe not start of class, but sometime tomorrow we'll start sequences. Anyway, the point is, this goes to infinity. That goes to infinity. It's not indeterminate. It just blows up. All right? So we remove the infinity minus infinity type just by factoring t out, is what happened here. Algebra alone was enough. This is clearly infinity. Which is kind of a mysterious thing because, you know, if you look at the graph here, it's 0, right? And then it's, I don't know, it doesn't, the thing is, the graph gets shallower and shallower, but on the other hand, it just keeps growing, right? So the area diverges under that, under y equals log x. Well, I probably shouldn't put the last. Okay. I guess what I was, well, sorry, not a great example. It's still not your example. I still haven't done what you want yet. Example 3, integral from 1 to infinity of dx over x. Here we go. Limit, t goes to infinity. You know what happened is I got in my mind the, I got confused what I wanted. I wanted this one, but I wrote that one. It's easy enough to do. They're related, right? In the following way. Of course, the log of 1 is 0, and natural log of 1 is 0. Natural log of t goes to infinity. And this is a little bit kind of surprising in some sense, because in example 1, we had something that looks kind of similar, right? I mean, what's the graph of 1 over x look like from 1 to infinity? I mean, to the casual observer, it's not so different than this one, right? It's not so different, right? mean, certainly this goes to 0 as x goes to infinity, right? Just like this one, we had e to the minus x goes to 0 as x goes to infinity, right? Apparently that is not enough to make the area under the graph be finite, right? It didn't go to 0 fast enough. The area is still unbounded under that shape. That area is unbounded, whereas this area was 1. Does that make you uncomfortable? Yeah. This is what calculus is here to sort out for us. These kinds of non-common sense things here. I mean, common sense, excuse me, common sense I think would kind of tell you that both of these should be infinite area, right? I mean, it's got an infinite side. How can the area be finite? Come on, right? Then common sense would just say both of these have infinite areas. And yet, no, not under the technical definition of area, which is given to us by integral. Oh, so tomorrow I will show you more about these. Here, let me just throw one of them up here. Something like this. Something like that. Looks innocent enough. But the thing is, at 0, it's not defined. Right? The integrand has a division by 0 on one of the endpoints. So how do you make sense of that? We'll talk about that tomorrow. Thanks, guys. Yeah, go for it. Just, you don't have to unplug it or anything. Just